Hi everybody, today I'm going to present a research paper on multi-defender security games with schedule. Here we will study security games featuring multiple defender and schedules simultaneously. We will show that unlike prior work on multi-defender security games, introduction of schedules can cause non-existence of equilibrium even under restricted environments. Going through the outline of this research paper, we will first see the introduction, then the research objective, then the motivation behind this research paper, the related works, the problem statement, analysis, the experiments that we have conducted, and the quality of Nash-Stackelberg equilibrium. To introduce this research paper, first I'd like to give an overview of an Stackelberg security game. In this strategic scenario, one player takes the role of a leader, making decisions before their counterpart, the follower, has a chance to act. The leader strategically anticipates how the follower will react to their decisions, aiming to maximize their own gains. This sequential decision-making process often yields different outcomes compared to situations where decisions are made simultaneously. The paper makes significant contributions to the field of multi-defender security games with schedules. Its key contributions include establishing existence of Nash equilibria in such games, shedding light on the equilibrium solutions in complex security scenarios, developing efficient computational algorithms to compute Nash equilibria, providing practical tools for analyzing and solving multi-defender security games with schedules. The proposed algorithm demonstrates practicality through efficiency. It efficiently computes Nash equilibria in multi-defender security games with schedules, enabling timely decision-making in real-world security scenarios. Then we move on to scalability. The algorithm's performance scales effectively with varying parameters such as number of targets, schedules, defenders, ensuring applicability to diverse and complex security environments. Then we move on to the objective of this research paper. The objective of the research paper includes to investigate multi-defender security games with schedule, to establish existence of an equilibrium under the specific assumptions, to develop efficient algorithms for computing equilibrium strategies, and analyze quality and efficiency of computer strategies through experiments. Motivation for multi-defender approach. In real-world scenarios, the landscape of security is often complex, involving multiple entities tasked with safeguarding against various threats. One of the central challenges lies in coordinating these heterogeneous defenders effectively, with different priorities, resources, and operation procedures aligning their efforts become paramount. This coordination challenge can lead to inefficiencies, overlap, or even gaps in security coverage, leaving vulnerabilities exposed. Addressing these challenges requires innovative approach that not only consider the diverse capabilities of each entity but also facilitate seamless collaboration and communication among them. Only by overcoming these hurdles can we ensure comprehensive and robust defense strategies that effectively mitigate emerging threats in an increasingly dynamic security landscape. Previous related work to this research paper are the research conducted by Liu et al. And Gan et al. That explores the dynamics of multiple defenders, scheduling, and the existence of equilibrium security games. However, these studies have certain limitations, such as overlooking the practical implementation challenges, simplifying assumptions that may not hold in real-world scenarios, and lacking comprehensive analysis. The multi-defender approach lays emphasis on collaboration and coordination to maximize overall security and minimize the likelihood of a successful attack. This emphasizes the importance of collaboration, coordination, synergy among multiple entities involved in security operations, highlighting the need for effective communication, shared resources, strategic alignment to achieve common security objectives. Explanation of Nash-Stackelberg equilibrium with scheduling. In this framework, defenders commit to schedules shaping attacker behavior. The Nash-Stackelberg equilibrium emerges as defenders anticipate the attacker response by choosing schedules. Attackers then optimize their strategies in response to defender schedules. This equilibrium encapsulates the dynamic interaction between defender commitments and attacker reactions within security games constrained by scheduling considerations. Moving on to the problem statement, the research paper addresses the challenges of incorporating schedules in security models. To understand the implication of scheduling on strategic interactions among multiple defenders and attackers, it investigates the computational complexities introduced by multiple defenders and schedules, seeking to develop effective algorithms for computing equilibrium solutions in complex security games or environments. Analysis and algorithms. In this research, we delve into the intricate dynamics of multi-defender security games with schedules, shedding light on the complexities that arise when defenders commit to specific schedules. Our analysis and algorithms contribute significantly to understanding the existence and computation of Nash equilibria in such settings. By exploring scenarios like randomly generated schedules, public security on grids, patrolling on layered networks, we uncovered practical challenges associated with computing NSE, particularly as parameters of T, SI, and network size escalate. Additionally, we introduce important assumptions like the subset of a schedule is also a schedule, which enhance our understanding of equilibrium concept in these security games. Through our findings, we aim to provide valuable insights into the strategic interaction between defenders and attackers in real-world security environments. Assumption 1. Clearance constraint. The text introduces a clearance constraint which ensures that defenders fully utilize their defensive resources. This means that the sum of coverage over all targets must equal the total defensive resource available to the defender. Theorem 1. The proof provides a sketch of why this strategy profile constitutes a Nash equilibrium. It argues that if defenders are seen as placing pressures to attract the attacker, the most robust solution to attract an attacker on target T is for all defenders to concentrate their resources on the target. This concentration of resources on a single target maximizes the incentive for the attacker to choose that target. In other words, there must be at least one strategy profile where each defender concentrates their resources on a single target to maximize the incentive for the attacker to attack the target. Then we have an assumption. Reusing example 1, the authors can claim that strategy profile V1, V2 constitutes a Nash-Stackelberg equilibrium. This claim is justified by showing that both defenders' coverage vectors belong to their respective feasible sets, and that no unilateral deviation by either defender can induce a change in attack target. Specifically, for defender 2 to improve its position, it would need to induce target 3 to be attacked. However, this would require increasing coverage on target 1 and 2 to be greater than 3, which is impossible given maximum coverage achievable on those targets. Similarly, the coverage induced by defender 1 on target 2 is higher than any coverage induced by defender 2, so no unilateral deviation by defender 1 can induce a change in the attack target. Therefore, since no defender can unilaterally improve their payoff by deviating from proposed strategy profile, it satisfies the condition of Nash-Stackelberg equilibrium. The following is an example of a Nash-Stackelberg equilibrium game. Now we'll find more about the existence and the computation of Nash equilibrium. First, we'll be applying lemma 1 to each defender that guarantees each Nash equilibrium must correspond to a Nash equilibrium with zero coverage on T. If we knew the attack target T, we can reduce our search to coverage profiles with zero coverages on T. Lemma 2 allows us to transform any Nash equilibrium into a new Nash equilibrium by adjusting V1 appropriately. Clearly, a similar process can be done for defender 2 and V2. Applying lemma 2 for both players yields coverage with simpler structures. Theorem 2 takes example and explain NC exists due to algorithm 1 and algorithm 2 serve two different purposes and operate on different inputs and outputs. Here is a breakdown of their differences. Algorithm 1 is Nash equilibrium for two defenders. Its purpose is to aim to find the Nash-Stackelberg equilibrium for a security game involving two defenders. Its input include the number of targets, the feasible coverage sets for each defender. Output: the output is an NC in the form of a tuple, where V1 and V2 are coverage vector for two defenders and T is the target chosen by the attacker. Operation: the algorithm iterates over each target T and computes a maximum coverage for each defender with respect to the target. Then it checks if the maximum coverage value satisfies certain condition, and if so, construct the coverage vector for the defenders accordingly. Algorithm 2 is max-min-conv. This algorithm calculates the maximum coverage for a single defender over a given set of targets. The input consists of defender schedules Si and a set of target T. The output is a maximum coverage value for the defender over a specified set of targets. The algorithm formulates and solves linear programming problem to find the maximum coverage value H defenders can achieve while ensuring that the coverage on each target is no greater than the minimum coverage induced by any schedule in the defender's feasible set. In summary, algorithm 1 is used to find the Nash equilibrium for a game with two defenders, while algorithm 2 is used to compute the maximum coverage for a single defender over a given set of targets. They have different inputs, outputs, purpose and context of security game optimization. Then we have the efficiency of Nash equilibria. This passage highlights the potential issue that can arise when applying algorithm 1 to Nash-Stackelberg equilibrium in security games. Let's break down the explanation. Blindly applying algorithm 1 can lead to pathology where the target chosen by attacker is in the Nash equilibrium is for undesirable for both players. In other words, there may exist a Nash equilibrium where both defenders would prefer to be a different target or attack a different target. This situation occurs when both defenders have non-negative coverage on chosen target, even though they strictly prefer another target to their attack. For example, consider a scenario where defender 1 prefers target 1 over target 2 and both target 1 and 2 over target 3. Similarly, defender 2 prefers target 1 over target 2 and both targets 1 and 2 over 3. Both defenders possess identity schedules, meaning that they allocate their resources equally across all targets. If both defenders allocate their resources equally, then the resulting Nash equilibrium is where target is a target where attacker chooses target 2. In this Nash equilibrium, neither defender can increase their coverage on target by deviating from the strategy. However, both defenders prefer target 1 to be attacked instead of target 2. Then we have our experiments for this research. Our objective revolves around assessing the practical computation of Nash equilibrium in realistic environments. We delve into scaling of computational time and explore qualitative aspects of NSE. Additionally, we compare quality of outcomes between multiple defenders and single defender scenarios. To achieve these goals, we analyze games generated through various methods, including randomly generated schedules, public security on grids, and patrolling on layered networks. Computational cost. We dwell into assessing the computational cost linked to discovering Nash equilibrium in multiple defender security games with schedules. Through our comprehensive evaluation across various scenarios, encompassing randomly generated schedules, public security on grids, and patrolling on layered networks, we unveil a notable trend. As parameters such as T and S network size escalate, there is a disequitable superlinear rise in computation time, underscoring the intricacies of managing large-scale securing environments. To compute the quality of Nash-Stackelberg equilibrium for each of these settings, we run the experiment 100 times and report the frequency of each rank suboptimally. In the end, I would like to conclude that the research paper establishes the existence of Nash equilibria in multi-defender security games with schedules, enhancing our understanding of strategic interactions in security settings. It also introduces efficient computational algorithms for finding NSE, providing practical tools for analyzing and designing security strategies in complex environments. Thank you and have a nice day.